Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Fermi Energy. Let's begin. Fermi Energy. The energy value up to which all the energy states are filled at 0 Kelvin and above which all the energy states are empty is known as Fermi energy. Let we consider a system. This is a system where fermions are there. Fermions, example of fermium, let electrons are there. And the energy level of the electrons like this. At 0 Kelvin temperature, at 0 Kelvin temperature, the energy levels are filled. As we know, fermions means here we consider electrons obey Pauli exclusion principle. According to Pauli exclusion principle, there can be only one electron in one energy state. So, in these energy levels, one electrons are filled. Finally, at a given point or at a given energy state, all such electrons are filled and that highest energy level is called the Fermi energy level. That energy level is called Fermi energy level and is given as UF. Here ground state at 0 to up to UF. In these energy levels, the electrons are filled, and above that of Fermi energy level, the energy levels are empty. So, as we write, what is Fermi energy? The energy value up to which all the energy states are filled at 0 Kelvin. At 0 Kelvin temperature, the energy states are filled and above which all the energy states are empty. Above which all the energy levels are empty, then that energy level, this energy level is called Fermi energy level. Okay. Let me explain it. As the temperature of the system decreases, the energy of electron gas also decreases. The energy of electron gas becomes minimum at absolute 0, which is at T is equal to 0 Kelvin. At absolute 0, the energy state with lowest energy are filled with electrons. How these electrons are filled? Now, in accordance with Pauli exclusion principle, there can be only one electron in one energy state. Therefore, starting from the lowest energy state, all the energy states contain one electron. Is the total number of electrons are filled. Let the energy of highest state occupied by the electrons be denoted by UF, which is called Fermi energy level. And more than that of Fermi energy level, the energy states are empty at absolute zero temperature, at 0 Kelvin. Fermi energy level is the highest energy level that an electron can occupy at absolute 0 Kelvin. In this way, we define what is Fermi energy and what is Fermi energy level. Mathematically, we calculate the value of Fermi energy. Suppose that all the electrons have their energies at 0 to UF maximum value. Since fermions obey Pauli exclusion principle, one phase space cell is to be filled by only one electron. Thus, the total number of electrons will be equal to the total number of phase space cells. As electrons are fermions, and they obey Pauli exclusion principle, that what Pauli exclusion principle indicate? Only one electron in one energy state. There can be only one electron in one energy state. So, the number of particles, so the total number of particles are equal to total number of phase cells. The total number of phase cells. Therefore, total number of particles n now given as total number of phase space cells. Total number of phase space cells we calculate GU du, and that energy value from 0 to UF, 0 to UF. In the previous video, we derived the expression for GU du, the value of GU du. Now put it integration from 0 to UF, the value of GU du as 8 root 2 pi v m to the power 3 by 2 divided by HQ into u to the power half du. These are the constant terms to outside 8 root 2 pi v m to the power 3 by 2 divided by SQ u half du. So, 0 to uf u half du. Its integral can be solved 8 root 2 pi v m to the power 3 by 2 divided by hq, that is u to the power 3 by 2 divided by 3 by 2 using the limit from 0 to uf. So, it will be 8 root 2 pi v m to the power 3 by 2 divided by hq into 2 by 3. Here u to the power 3 by 2 upper limit minus lower limit, it will be uf to the power 3 by 2. From that, uf to the power 3 by 2, uf to the power 3 by 2 is equal to, the terms are multiplied. So, the expression will be 3 n hq divided by 8 into 2 16 root 2 pi v m to the power 3 by 2, or u f is equal to 3 by 2 this side, the power of 2 by 3, here hq divided by m to the power 3 by 2. So, the result will be h square divided by 2m 3n divided by 8 pi v to the power 2 by 3. That is the expression for Fermi energy. This is the expression Fermi energy. Let me consider a metal. In that of metal, there are free electrons. So, how we can express in terms of free energy? For a metal, let rho is equal to n by v, total number of particles to the volume, that is the number of electrons per unit volume, which is also called as the concentration of free electrons within that of metal, that is the concentration of free electrons within the metal. Okay. At that of given temperature, now the expression for Fermi energy will be how much? Look here, if we take in that way uf 3 by 2 uf to the power 3 by 2 is equal to 3 n h cube divided by 16 root 2 pi v m to the power 3 by 2 m to the power 3 by 2. So uf to the power q, squaring both sides, that side 9 n square h to the power 6 divided by its square as 256 into 2 pi square v square m cube, or u f is equal to cube root 9 n square h to the power 6 divided by 256 into 2 512 pi square v square m cube to the power 1 by 3. Again simplifying it, we have uf is equal to 9 rho square h to the power 6 divided by, in place of n by v we substitute rho, n by v we substitute rho, 5 1 2 pi square m cube to the power 1 by 3. That is the expression for Fermi energy in case of a metal or a conductor. Look at the expression. There will be no such term of volume. Therefore, we can say that Fermi energy is independent of the size or the volume of the conductor, but it depends upon its density rho, that is the concentration of free electrons within that of metal. This is the expression for Fermi energy. This is the expression for Fermi energy of a metal or conductor. Expression for Fermi energy of metal or conductor. Again, the energy distribution among the electrons present in that of metal or conductor can be calculated, which is Nu du. The expression for Nu du, as we know, that is 8 root 2 pi v m to the power 3 by 2 divided by h cube u to the power half du divided by e to the power alpha e to the power u divided by kt plus 1. So, in place of that quantity Nu du, in place of this quantity we can write that the quantity will be 3 by 2 n uf to the power 2 by 3. Instead of that term we write 3 by 2 n uf to the power minus 3 by 2 u to the power half du divided by e to the power alpha e to the power u by kt plus 1. This is the expression for energy distribution among the electrons present in that of metal in terms of Fermi energy. The energy distribution electrons inside that metal, the energy distribution of electrons inside that of metal in terms of free energy. The expression for this is the expression of the energy distribution of electrons inside the metal in terms of Fermi energy, not free energy, that is Fermi energy. Fermi energy expression. So, here with the help of this video lecture we understand the concept of Fermi energy, what is the Fermi energy and the expression for Fermi energy. Now, for a metal, the value of Fermi energy and energy distribution in terms of Fermi energy. It is an example here. Here is the example. So, with this useful and informative notes, let me wind up the session. Thank you.